Hi there! If you've stumbled on this video, welcome. It's not a main lesson, I'm just here to try and prove a result to you about the sum of the first n square numbers. The reason I'm doing this video isn't because there don't exist another 101 proofs or even better, nicer looking proofs than one I'm going to give you already on YouTube. You could have found this yourself without coming to one of my videos. But I'm just going to try to do one myself to make it hopefully quite accessible so you can see this result for how you add up the first n square numbers. So the result I want to prove, and I'm going to prove, is this one here. That if you add up 1 squared plus 2 squared plus 3 squared all the way up to n squared, where n is some integer, you get 1/3 n cubed plus a half n squared plus 1/6 n. So I'm going to just show you this just using some actual numbers. So let's just add them up. So first of all, the first value of the sum would be 1 squared, which should just be 1. The next number in the sequence would be 1 squared plus 2 squared. So 1 squared plus 2 squared is 1 plus 4, which is 5. The next one, 1 squared plus 2 squared plus 3 squared, 1 plus 4 plus 9 gives us 14. So each time we just added on the next square number. So the fourth number, we add on 4 squared. That'd be 30. Then plus 5 squared is 55. Plus 6 squared plus 36 gives us 91. And then plus 7 squared plus 49 gives us 140. And so on and so on. Okay, so when n is 1, we have that, 2, 3, 4, 5, 6, 7, and so on. So for example, the sum of the first 6 square numbers would be 91. So I'm going to link this back to the nth term. So GCSE work, the nth term. It'd be stuff like 4n plus 2 or 3n minus 7. When the gaps between the numbers are constant, it's a linear sequence. So let's compare the gaps between these numbers. So between 1 and 5, that's a gap of 4. Between 5 and 14, that's a gap of 9. You can see already these gaps are increasing. Between 14 and 30, that's a gap of 16. Gap of 25. Gap of 36. And the last one's a gap of 49. And so if the gaps were constant between the terms, that would be a linear sequence. The gaps aren't constant, so it's not linear. So let's compare the gaps of the gaps. So between 4 and 9, that's a gap of 5. Between 9 and 16, that's a gap of 7. Between 16 and 25 is a gap of 9. The next gap of the gaps is 11. The final gap of the gaps I'm going to show you is 13. Now again, these gaps of the gaps are increasing. If the gaps of the gaps were constant, that would have been a quadratic sequence. Because the gaps of the gaps aren't constant, it's not quadratic. However, if we do the gaps of the gaps of the gaps, the gap between 5 and 7 is 2. Between 7 and 9, that's a gap of 2. From 9 and 11, that's a gap of 2. You can see now the gaps of the gaps of the gaps are constant. So it's not linear, it's not quadratic. We've now got the gaps of the gaps of the gaps are constant. Therefore, we know this sequence is cubic. So we're looking for a cubic sequence. So what we do now, the general form of a cubic, we need to write down. So any cubic can be written in this form. an cubed, where a is some constant to be found, plus bn squared, where b is some constant to be found, plus cn plus d. So we need to solve this, and if we solve it, we can then prove the result. Okay, so let's just substitute in what we know n to be. So let's try when n was 1. So when n is 1, let's substitute in what this gives us. Well, the first term, when n is 1, the sequence was 1. So 1 must equal a times 1 cubed. A times 1 cubed is just a. plus b times 1 squared. 1 squared is just 1, so that's plus b. C times 1 is just c, plus d. So when n is 1, this needs to hold. Next, just think about when n is 2. When n was 2, that gave us 5, and so 5 must equal this expression when we substitute 2 into it. So when n is 2, a times 2 cubed gives us a times 8, so that gives us 8a. b times 2 squared, that's 4b. c times 2 gives us 2c, and then finally d. So we can carry on and do this for n equals 3. The third term of the sequence was 14. So 14 must equal a times 3 cubed, that's 27, plus b times 3 squared, which is 9, plus c times 3, 3c, plus d. And let's do one more, then we're going to get some simultaneous equations coming out. The fourth term was 30. So when n is 4, that gives us a fourth term of 30. So 30 equals a times 4 cubed, that gives us 64. Plus b times 4 squared, that gives us 16b. Then plus 4c plus d. So let's look at these and compare. So let's look at these two first of all. So if we do this bottom equation, subtract from the top, 5 take 1 gives us 4. 8a take away 1a gives us 7a. 4b take away b gives us 3b. 2c take away c gives us 1c, and the d's cancel. So we now have a new equation in relation to just a, b, and c. Let's do the same with these two, when n is 2 and n is 3. And so here what we're going to do is this equation subtract this one. So first of all, the start becomes 14 take away 5, that becomes 9. 27a take away 8a, that gives us 19a. 9b take 4b gives us 5b. 3c take 2c just gives us 1c, and yet again the d's disappear. And let's do it yet again for this third equation and the fourth equation. And so the bottom subtract this one above it. So 30 take away 14 to give us a third equation. We get 16 equals, now the a's, 64a's take away 27a, that leaves us with 37a. 16b take away 9b, that gives us 7b. 4c take 3c just gives us 1c, and again the d's cancel. Now let's hone in on these two and subtract the top away from the one below. So we're going to do this equation, subtract this one. So 9 take 4 gives us 5. 19a take away 7a gives us 12a. 5b take 3b gives us 2b, and the c's cancel. So we're making progress slowly. Let's do the same for this one. So this equation, take away this one. 16 take 9 gives us 7. 37 take away 19, that gives us 18a. 7b take 5b gives us 2b, and again the c's have cancelled. So we've gone from having 4 unknowns here to just 2 unknowns. So we now have a simultaneous equation in 2 unknowns. We can now finally make some progress in solving this. So yet again, If we do the bottom one, take away the top, 7 take away 5, that gives us 2. 18a take away 12a gives us 6a, and the b's disappear. And so 2 equals 6a. Divide through by 6, therefore a equals 2 over 6, which is a third. So we now know that a is a third. So we can substitute this back in. And so if we sub a into this equation, so if I sub a into the blue, let's just say, where the blue equation, sorry, the blue one I'm just going to highlight here. Okay, this now becomes 5 equals 12 times a, so 12 times a third, plus 2b. So 5 equals 12 times a third is 4, so 4 plus 2b. That can now be rearranged. We now get that b must be a half. Now we know that b is a half, we can now substitute this into, for example, this equation. So if we substitute that, if we sub a then b into the purple equation, I can pick any one now, really. I can pick, say, this one. Okay, so we'd now have that 4 equals 7a. Well, if a is 1/3, 7a is 7/3, plus 3b. If b is a half, 3b is 3/2, plus c. Therefore, we get that c is 4 take 7/3 take 3/2. So let's just work this one out. So 4 take 7/3 take 3/2. That gives that c is 1/6. So we're almost there, we just need to think about what d is. Okay, so now we substitute in a, b and c into one of the starting ones. Sub a, b and c. I can put this one here into the equation for when for n was 2. I could pick when n is 1. I'm just being lazy because n equals 2. This equation is on the screen. So the equation for when n is equal to 2 is this one here. So that equation, we get 5 equals 8a. So if a is a third, 8a is 8/3. Plus 4 lots of b. Well, if b is a half, 4b is going to be 2. We worked out what c is. C was a 1/6, and so 2c will be 2/6, which is 1/3, because 2 over 6 simplifies to 1/3. Then finally, plus d. But if you look here, 8/3 plus 1/3 is 9/3, which is 3, and 3 plus 2 is 5. And so 5 equals 5 plus d. And so therefore d is actually going to be 0. So the equation an cubed plus bn squared plus cn plus d we can now simplify and by putting in a, b and c. So an cubed plus bn squared plus cn plus d. Well, d is 0, so that just goes. We had c as 1/6. We had b is a half. Oops, that's the wrong colour, my mistake. And we had, from earlier, that a, look, was 1/3. So just plugging these values in, we have a, which is 1/3, n cubed, plus b, which is a half, n squared, plus c, which is 1/6, plus d, which is 0. And so we're left with this result. And this result is the sum of the first n square numbers. 1/3 n cubed plus half n squared plus 1/6 n, which is exactly what we wanted to prove at the very beginning. And so we can work this out by just doing lots and lots of simultaneous equations, and it all drops out if you're patient. So in terms of if you need to prove this in an exam, I very, very much doubt it, but there's the result in case you wanted to know if it really is true and you wanted to convince in. I think it's a good thing to be convinced rather than just accepting things on face value. So anyway, that's it done. Thanks for listening if you have listened, and cheers for tuning in.